I hope you will enjoy the last talk in the KubeCon, at least for the runtime track. So a little bit about myself. My name is Eran Yanay. In the past few years, I work at Twistlock, where I've been a software engineer and now a team leader. This is my email. You can feel free to reach out later if you don't have time for the questions. So the first question for today is, how many of you are familiar with what it does? No one? OK. How many of you ever ran this command? And you have no idea what it does. OK. So I'm going to cover many topics about CNI plugins today and CNI in general. And hopefully, within a few slides, I will get back to this example, and you will have a better understanding of what it does. So the agenda for today is to eventually understand how to write a CNI plugin from scratch in Bash using only simple command line tools. And we'll start with an overview of what CNI is. We'll continue with understanding how it's been used in high level in Kubernetes, what it does when it operates, and eventually we will conduct a small demo that demonstrates everything that we will soon see in this talk. So what is CNI? CNI stands for Container Networking Interface. It's the interface between the container runtime, in our case, Kubernetes, and the network implementation. When the CNI plugin is running, it is responsible for configuring the network interfaces and possibly routes. And also, another thing that worth understanding is that the CNI plugin concerns itself only with the networking connectivity of the pod. This is the link to the latest CNI spec. It's 0.4. You can follow the link and read further about it. For the rest of this talk, I'm actually going to focus on the latest, on the previous spec, which is 0.3.1. There aren't many crucial differences between them. For what we are going to touch in this talk, it's going to be practically the same. The only reason that I'm doing it is for the sake of the demo, which for Kubernetes 1.14 is still referencing the old spec. So CNI plugins are often composed of two components. The first component is the CNI binary, which is the plugin itself, the thing that is implementing the interface. And when it's running, it is being executed by the kubelet and is responsible for configuring the network interface. It's the part that sets up the connectivity of the container. The second part is the daemon, where essentially most, if not all, CNI providers for Kubernetes, they also provide a daemon that is going to run on every node in the cluster. And when it is running, it will be managing the reachability of your pod throughout the entire cluster. Reachability means that every pod is accessible or reachable from every node. And when talking about networking in Kubernetes, it's not such a trivial task because we're talking about virtual addresses that are local to each node and are not necessarily known at any point in the cluster. Meaning that if you have two nodes, then each node is allocated with some address space for its pods, and this address space is virtual and known only to the node that is responsible for this address space. So for the rest of this talk, I'm going to focus mostly on the first part, which is the CNI implementation itself, meaning that we will see code examples and talk about the way that the pod acquires its network interface, being assigned with an IP, and so on, and leaving the general reachability about like cluster reachability, internet, and so on. We will leave it for the end of this talk for the demo, and then we'll experience the problems that arises there. So just to make it clear, the CNI binary itself is only composed of those two components. So on the left, you can see a configuration file, which is simply a JSON file, JSON formatted file. It contains a few required fields, such as the CNI version, which references the spec that the plugin is fulfilling, the name, which is the plugin name, and the type, which is the name of the binary to look for in the folder that holds all the CNI binary implementations themselves. It can contain also additional optional fields, which I'm not going to discuss about today. They are not shown here as well. And it can contain also custom fields. In this case, I'm showing an example of the pod slider, which is a custom field which I decided to put in the config. And we will soon see why I chose to put it there and how I'm going to use it later on. On the right is the implementation itself. It's a binary executable. In this case, I decided to do it in Bash. And for the 0.3.1 specification, it has to support those 4 commands. The add command, which is called when the CNI plugin is executed for configuring networking interfaces for a new container. The delete command, which is called when a container is being deleted and now we need to possibly perform some sort of cleanup, maybe release an IP, perform some other operations regarding our own implementation and what we chose to do. The get command is rather ambiguous. I'd rather not to talk about it today at all. It was also changed in the 0.4 specification to check. And the version command, which is simply, it's trivial, it just returns the plugin version. So going back to the Weave example that I've shown you before. So the command that we've seen simply downloads the YAML file and runs it. And what is in this file is simply a demo set implementation, a configuration. And you can notice that it's going to run the host network, and this is important for CNI plugins because, one, it allows us to deploy them even before a CNI plugin is configured, and then we don't need an IP to be allocated for us, so our deployment can run everywhere even when the environment is still not ready. And the second reason for being on the host network is, of course, because we are going to manipulate the host network stack by performing some maybe IP table changes, routes, and other stuff, so we need to run the host network. And there's a second thing worth noting here is that you can see that the Weave container itself, it has mounts to specific paths on the disk, to the locations where we need to place the configuration file, and what happened now? Just a second. I didn't do anything. Okay, almost. Okay, so you can see that the Weave container is going to have mounts to the specific folders in the disk that are going to hold the CNI binary itself and the configuration file. And when it's going to run the LAN script. So if we take a deeper look at the LAN script, you can see that eventually it's going to do multiple things, and then it's going to make some preparations, such as make sure that the CNI binaries folder exists, create the CNI net.d, which is the location for the configuration itself. And eventually it's going to deploy the files in the appropriate locations. So now that we have a rather simple but good understanding of the overview of what CNI plugins is, let's see how it's being used in Kubernetes. So a new pod is scheduled to run, and then the API server is going to communicate with the kubelet, and it's going to give it configuration about the pod, and it's going to tell him to schedule the pod, right? So the next step that's going to happen is that the kubelet is going to set up the pod network namespace. Can anyone guess how it does it? Okay, so it's going to set up the parse container. The parse container, which I assume most of you or all of you are familiar with, it has a couple of roles. One of them is to maintain the pod network namespace. And once it is initialized by the CNI plugin, it is going to be shared across all the containers in the pod. And then they can properly communicate with whoever they need to communicate with. Now, at this point, the pod network namespace only has the loopback interface. And the next thing that's going to happen is that the kubelet is going to invoke the CNI plugin. It's going to tell him, there's a new pod that I need to set up, here's the details about it, and configure it. And then the CNI plugin is going to do multiple things. It's going to create the interface, the network interface for the pod. It's going to allocate IP for it, possibly define some routes and do other network preparations. And then when it is done, the pod namespace is ready, and it's going to be shared across all the containers, and they will properly be using it for other connectivity. So let's see how the CNI plugin is being actually used by the kubelet. So it's going to receive information in two different forms. The first piece of information that it receives is the container info. So the container info is received by environment variables, and it contains information such as the command, in this case, add, for adding a new container, the container ID, which is the unique identifier of the container, the netNS, which is the path on the disk in the proc file system for the network namespace of the container, and the name of the interface that we want to assign to it. The second piece of information is the CNI config, which is essentially all the content of the CNI config file that we chose with all the fields that we chose to embed in it. And it is received via the standard input. At this case, at this point, the CNI plugin is going to do multiple things, and it's going to set up the network interfaces according to the given spec, according to the given configuration, and eventually it's going to output to the standard output, indicating to the kubelet the things that it has done, such as the list of interfaces that it set up, their MAC address, their name, their default gateway, the IPs, and so on. So let's take a deeper look at the internals of what the CNI plugin is actually doing. So each pod has its own network namespace, and an easy way to connect the pod network namespace to our host is to set up a bridge and connect the pod into the bridge. You can think of the bridge as a physical switch that when you take the pod and connect into it, it's like if you were taking a wire and connecting it to one of the switch ports. So in order to connect it to the bridge, we are going to create something called the VIS pair. The VIS pair, Virtual Ethernet Device Pair, is a pair of virtual Ethernet devices that are created in pairs. They are interconnected pairs that are basically, when you are creating them, every packet that is sent at one side is immediately received at the other side. So a very good use case for those pairs in Linux in the scope of containers is that we can take one end of the pair and put it in the pod network namespace and keep the other end at the host network namespace. And then they can act as tunnels across network namespaces, connecting the pod to the hosts. So we took one end, we connected it to the pod, and the other end we kept in the host, connecting it to the bridge. And at this point, any packet being sent from the pod is immediately received on the host at the bridge. And then at this point, most of the work is done. Every pod that is going to be scheduled to run will be, the CNI plugin will be called, and it will set up the virtual Ethernet devices pair, connecting it to the bridge, setting up an IP for the device, and then with the help of common Linux tools such as IP routes, IP tables, and others, we are going to make the appropriate routes for traffic to flow correctly to the pod and from the pod to other pods in the cluster. So now I'm going to go even lower to the technical details. So on the right, we can see an example for an environment that I have currently running on my laptop that I'm going to use later for the demo. It has two nodes, node 1 and node 2. Each node, both nodes communicating over the ENP network interfaces over the 10.10.10 subnet. And when I created the cluster, each node got allocated with some pod address space for the pods that are running on this node. So for node 1, it received the pod address space to be 10.240.0.0.24, and similarly for node 2. So the config that I need, that I decided to create here is a config that says, that holds the port sider. The port sider for the specific node is going to be different for every node that I'm going to connect in my cluster. So the port sider will be 10.240.0.0.24. This is the example of the config in node 1. And this is the skeleton for the CNI executable itself. So for the rest of the few slides, I'm going to focus on the add command. So as we said, the first thing that we want to do is to set up the bridge. So I'm going to calculate the port sider, which is by extracting the config, which resides in the standard input. So I'm going to cut the standard input, pass it to the JQ tool, which is a simple tool to manipulate JSON strings in Bash. And I'm going to take the port sider from it. Once I have the port sider, I'm going to do just some manipulation on it to calculate the gateway address, which is going to be the address of the bridge. And then I'm going to use the bridge utils package, which contains the brctl command line tool, to create a bridge. I'm going to create a bridge that is called CNI 0. Then I'm going to enable it, bring it up, and I'm going to set it with the IP of the port sider gateway. So the bridge on the node is going to contain the first IP in the address space of the port siders. The next thing that I need to do is to create the whisper. So I need to calculate a name for a random name for the device that is going to reside on the host, because it has to be unique. I'm going to use the IP link command to create the pair. I'm going to say, create a whisper with one end called CNI if name, which is the name that I was told by the kubelet, and its peer to be the name that I calculated for the host. And then I'm going to enable it. The next thing that we said that we need to do is to move the ETH0 to the pod network namespace. So something worth noting about network namespaces in Linux is that they exist in two forms. The first form is defined by the process and under proc, the PID name, and being discarded when the process dies. And the other form is under var and NS, which those network namespaces, they long-lived, they are created and they are deleted when we decide. They are not bound to any process. And what's interesting about those network namespaces is that they can be manipulated using the IP link command. They can be manipulated in a way that we can perform actions inside the network namespace, similarly to if we do kubectl exec or docker exec. So we can still manipulate the network namespace in this case is of the first case that doesn't reside in var and NS, but if we create a symlink into this folder, we can still manipulate it using this tool. So I'm going to set the symlink of the CNI NS from the proc folder under var and NS, and it's going to be called CNI container ID, which is the unique name of the container. Then once it's there, I can perform various actions on it, and in this case, first I'm going to use the IP link command to set ETH0. I'm going to set its namespace to be in CNI container ID. So in this case, at this point, ETH0 now resides in the pod network namespace. It's no longer part of the host network namespace. Then I need to calculate the IP. So you can see in the diagram, it's going to be something 0.2. And while there are many ways to calculate IPs from the point of view of the CNI, there are ready tools such as the DHCP and the host local and other means as well. I decided to do something that is very simple and is good enough for the sake of this talk, which is this. I'm simply going to use the file that is going to hold the last IP, and I'm incrementing it by 1 every time, update the file, and then I have the IP, and I can use it. And then I'm going to do some rather trivial operations. The first operation is I'm going to execute a command in the pod network namespace that brings the interface up. I'm going to assign the IP to it, so you can see I'm going to use IPnet and exec in the container ID, set the IP to the device CNI name, which is ETH0. And lastly, I'm going to set the route to be the default gateway, which is the bridge IP. So at this point, the CNI plugin is done, actually, and the pod is already connected to the bridge, and packets flowing from the pod are immediately seen in the bridge, as we seen previously. So a little bit about the demo before we start. As you already understand, there's no daemon implementation in here, so we only have the CNI plugin itself. Yeah. And I'm simply going to deploy a simple 3 pods that are going to run on both nodes, and we'll see what works and what doesn't. And for everything that doesn't work, essentially, in the common use case, it's going to be set up by the daemon. So for the demo, we'll just do it by hand. So this is my environment. We can see we have 2 nodes that are connected using the internal IP that I showed you earlier. And if to see the port side range, can you see it's good enough on the back? It's okay? Okay. Yeah. So node 1 got allocated with the port header to be 10.240.0.0, and node 2 with the 0.1. And I have a deployment that I'm going to run now. This is going to deploy an Alpine container that is going to run on node 1, an Nginx container that is also going to run on node 1, and another Nginx container on node 2. And I already have the CNI plugin installed before we started this talk, so by now I expect my pods to already have an IP assigned. Yeah. Okay, so all pods are already running, meaning that the CNI plugin was already executed. And you can see that the IPs are indeed incremented by 1 between them. You can see that Alpine 1 is with 0.5 and Nginx with 0.4. So I already expect a common, simple connectivity to be available from the host to the pod because they are already connected. So I'll try to communicate with my Nginx. And it already is working. But other stuff, such as communicating with Nginx 2, is not going to work. Similarly, we can try to communicate from Alpine to Nginx. So pod-to-pod communication in the same node is not working, and why? So the first problem is this. Every pod resides in a different network namespace, and traffic flowing from one pod to the other from the point of view of our host is considered to be external traffic. It's very similar to the case of where you have a router and you have multiple users connected to it, and you want to allow or drop packets flowing between them. In order to allow packets to flow from one pod to the other, we need to accept it. And we have something in Linux called, I assume most of you know, IP tables, and there is the forward chain, which is the one responsible for allowing such traffic. So if we investigate and look at the forward chain, consider that we have multiple rules. One of them belongs to Docker, which is practically doing something very similar to what we just seen. And there is no rule in here that says to allow traffic from our port side range. So let's add one. So I'm going to append to the forward chain a rule that says that anything that originates from my port side range, and I don't care about the accuracy, I can just say the port side range of the entire cluster, to accept it. And anything that is going to any of those IPs also accept it. And now I expect that this command will work. So we have pod Yeah, okay. Thank you. So pod-to-pod communication is already working, but we still have a couple of things to fix. The next thing that I want to show you, let's see the IPs again, is that communicating with other pods is still not working. We can try from here. It's going to be similar if we are going to try from the pod itself. It's not going to work. And the reason is that we said that the pod header in each node is known only to it, and it's not known to anyone else. And we need to instruct our kernel to say, if we have a packet that is going to nodes 2 IP address, then route it via nodes 2 IP address itself, from its pod header to its IP address. And the way to do it is with the IP route tool. So we can say IP route, add a route that routes anything going to nodes 2 pod header range, which is this, via nodes 2 IP address using this device, which is the device that they are connected with. And also, I need to do the same relative rule for nodes 2, which says route anything going to nodes 1 pod header range via nodes 1 IP address using the same device. And now this should work, or not. Just a second. Yeah, I need to apply the forwarding rule for nodes 2. Yeah, okay. So now we have packets flowing from pod to pod locally, and also from pods across the cluster itself. And the last thing that we want to fix is internet connectivity. So if I'm going to try to, for example, ping the internet, it's not going to work. And why? So in Linux, we have something called, we need to do, okay, so when we try to send these packets from the container, it's going to leave the container with the IP address of the container. And when the destination will receive the packet, it's going to see the IP address of the container, which is a private address, which it won't know how to deal with or how to reply back. The common way to fix this in Linux is by using SourceNat. SourceNat is a tool that allows us to replace the source IP in the packet when it leaves the host, so that when the packet leaves the host will change the source IP to the host IP. And then when the response arrives back to the host, it will replace it back and send the response to the container. This is something that is called masquerading, and we can apply a rule that says, add the rule to the IP tables, to the post-routing chain, which is the last chain that is going to evaluate outgoing packets that are leaving our host, and I need to add it to the NAT table. And every packet that originates from the pods, which is this pod header range, and it's going out not to the CNI bridge, meaning that it's going out to the internet. Masquerade it, meaning apply the source NAT. And then this should work. Okay. So usually everything that we did manually now is something that we will do using a daemon set or some sort of deployment or an agent or daemon that is going to run on every node, and it's going to do those kind of operations for us when it is running. And that's it. Thank you. So everything that we've seen, the CNI plugin itself and the configuration file and an example for the commands that we had to run manually. I put it all in this GitHub repository, so you can take a look later and play with it if you want. Any questions?
Okay, perfect.
Yeah.
Thank you. Thanks for this presentation. I was wondering if when you start, if multiple nodes, pods must be started on the same node, are the plugins invoked concurrently? So
what? Sorry.
Is there some issue if multiple pods must be started concurrently?
If they are started concurrently?
Concurrency issue in the pod, in the network.
If they are started concurrently, the pods? You mean if pods are going to start concurrently, if it's going to be a problem?
Yeah.
Well, in this example, I'm using the file, so both executions can possibly read the same IP, maybe, but eventually it's going to sort out because if the CNI plugin is going to fail, so it simply try to recreate the pod. But yes, it's a rather simple example, so things may go wrong. Also, I didn't show it, but the IP tables that I changed are also manipulated by other tools by the kubelet. So those rules are going to be removed after a few seconds or a minute or two because I didn't use a dedicated chain, for example.
Hi, I'm Junaid Ali. Thank you for the great talk and introducing us with writing simple CNI plugins. So this is similar to Calico, right? Because Calico works in a similar way. I looked at it a long time ago, but they are also using some route stuff and other things. So is this like Calico? Calico also works same, right?
Well, all of them eventually, the low-level details is going to be similar this way or the other.
Okay. And my other question is, so for the service discovery, for making the Kubernetes services to work, is this again some kind of IP tables magic that we have to apply?
Sorry?
For services, let's say we expose the pods using a service. So what do you think?
Yeah, it's going to work flawlessly because it's something that is not as part of the CNI plugin responsibility. I can just expose, say, my Nginx2 with port 800 and the target port to be the Nginx port. And if the rules aren't flashed already, so it should work.
Oh, that's cool. Thanks.
Any other questions? Okay, let's thank Mr. Eran. Yeah.
Thank you.